So now that we've seen how to decompose a rational expression that has purely linear factors in its denominator, we want to take the next step and look at how to handle a situation like this one, where there's a quadratic factor in the denominator. And I actually want to be a little more specific about that. It's a situation where there's an irreducible quadratic factor. If I could factor that thing down to two linear factors, then I do it because the linear factors are moderately easier to work with, and it's worth taking the extra step to factor it. In a situation like this, where that is a irreducible quadratic and it can't be factored any further, then here's what we're going to do. It's going to be very similar to what we did with the linear case. I'm going to start off just writing out the expression here: x squared plus 2x plus 5, x minus 4. Okay, we're going to handle the linear factor exactly the same as we did before. That's going to get an a over x minus 4 term. Now, it's the quadratic factor that we're going to handle just a little differently. That's also going to get a term up here in the numerator, obviously, but it's going to be a linear factor, not a constant one. So it's going to be bx plus c. And that really is the only change. From here, we're going to do the exact same sequence of steps. I'm going to clear the denominators. So we'll multiply by x squared plus 2x plus 5 times x minus 4. When we distribute this here, it becomes x squared minus 2 equals a times the quadratic factor, x squared plus 2x plus 5, plus bx plus c times x minus 4. So I'll multiply that side, the right side out. It says ax squared plus 2ax plus 5a plus bx squared minus 4bx plus cx minus 4c. And now we'll group the terms. Right? So I have a plus b times x squared plus 2a minus 4b plus cx plus 5a minus 4c. And again, that equals x squared minus 2. So if we equate the coefficients, a plus b is equal to 1. 2a minus 4b plus c. Well, there is no x term on the left side, so this is going to have to equal 0. And finally, 5a minus 4c is going to have to equal negative 2. Again, we've come down to a system of three equations and three variables. And even though some of the equations don't have all three variables, we should still be able to solve this. So what I'm going to do here, I'm noticing that these two equations both have an a and a c. Right? If I could get rid of this b term, then I'd have two equations in two variables. And whoa, sorry, I got carried away. That was 2a minus 4b plus c equals 0. And I'll be a little more careful. Let's get rid of these lines down here. Oh, I did it again. 5a, sorry, I'm making a mess. 5a minus 4c equals negative 2. Okay, so I want to get rid of that b term, and I can do this by solving this equation for b. So b is equal to 1 minus a, and if I substitute that into here, this becomes 2a minus 4 times 1 minus a plus c equals 0. All right, so what is this? What does this become? This is 2a plus 4a, so that's 6a. I'm going to get a minus 4 here, and I'm going to move that to the other side. So put a plus 4 over there, and a plus c there. Okay, so now this equation and this equation, two equations, two variables, excellent. I can work with this. If I solve this first equation for c, this is c equals 4 minus 6a. Substituting that into the other one gives me 5a minus 4 times 4 minus 6a equals 2. That's, let's see, 5a minus 16 plus 24a equals 2. So 29a equals, let's see, I'm going to add 16, well, that's a minus 2 over here. So we'll add 16. This becomes 14. A is 14/29. All right, so if we substitute that into this equation, I'm not going to make you watch me fiddle around with these fractions. C should come out equal to 32/29, and then we'd go back over here and do B. B is going to be 15/29. All right, so what does that make my answer? Well, we'll refer again back up to here, right? And we'll put A and B into that equation. And this becomes 14/29 times 1 over x minus 4. Plus, and I'm just going to pull the 1/29 part out and make this 1/29 times 15x plus 32 over x squared plus 2x plus 5. And there's my final result. Right? That's my partial fractions decomposition for this expression. Now, and again, I know I said this in the last lecture. Hopefully you watched that one. If you didn't, how I write the final answer, look at how your professor does it. If he wants to distribute these 29s into here, then okay, yeah, distribute it into there. I like to leave them out in front because I'm looking ahead. At the end of the day, we want to integrate this thing, right? And to integrate this thing, it's useful to just have as much of a constant as I can factored out in front, because then the integrals just kind of go in here, right? And we don't have to worry about those constant parts until the very end. This is the kind of the busiest case that we're going to consider here. It's a situation where we have a repeated quadratic factor. And the way we handle this is really just a very natural kind of combination of what we did previously when we had repeated linear factors and what we just did on the previous slide with quadratic factors. Now, I'm going to set this up, and I don't think anybody wants to sit and watch me go through some really rather messy algebra calculations. So I'm going to set this up, and I'm going to jump right to the final answer. In case you want to try to work out all the steps yourself, you're certainly welcome to. That way you have something to check your work against. So the way we're going to do this is I'm going to start with the original rational expression, 5x to the fourth plus 2x cubed, 18x squared, 18x, 58, all over those two polynomials, x squared plus 2x plus 5 squared times x minus 4. Okay, so we start the same way. The linear factor, we handle that the way we always handle linear factors. It's a over x minus 4. Plus, now I'm going to deal with that quadratic factor. Like I said, I'm going to do this the exact same way we did when we had repeated linear ones. I'm going to do bx plus c over x squared plus 2x plus 5 plus dx plus e over x squared plus 2x plus 5 squared. From here, you're going to follow the exact same procedure. You're going to clear the fractions. You're going to rearrange the terms on the right-hand side in terms of the individual powers of x. They set the coefficients equal to each other. And as you can see, right, we've got 5 variables. So you're going to end up with quite a few equations. Right, and it's solvable, right? You can do it, but like I said, I'm not going to ask you to sit through some really rather horrid algebraic calculations. But I will give you the final answer, right, in case you want to try to work through this on your own. This would be 2 over x minus 4 plus 3x over x squared plus 2x plus 5. So c came out being equal to 0 here. Plus negative x minus 2 over x squared plus 2x plus 5 squared. Okay, so as a practical matter, this is as high as I would ever go in a calculus class, right? And sorry, I'm getting a little ahead of myself. In the next lecture, I'm going to start by summarizing all of the methods that we've talked about so far. So you kind of have all those ideas in one place. And then I'm going to talk for a little bit about when you should think about using this method to solve the integral problems and when you should think about trying something else.